All right, guys, welcome to lesson 6. I'm going to talk about something called end behavior. So hopefully by the end of the day, you guys will be able to determine the end behavior, whatever that is, of a polynomial. We're also going to introduce you guys to some new mathematical notation, which is used for these things called limits. Okay, and that's going to be helpful with describing and writing our answers for this stuff called the end behavior. So first of all, I'm going to have us just brainstorm here for a second, so as to introduce a concept that's coming up. So let's go ahead and see what's going on here. So I've got a function up here at the top, y equals 2x plus 1. And basically, I have a table here, and we are plugging in values for x. Now, what I want you guys to notice is what number am I getting closer and closer to? In other words, what x value am I trying to approach here? I'm going from 1.2 to 1.4 to 1.6 to 1.8 to 1.9. What number am I trying to reach there? Hopefully, you guys recognize I'm approaching a value of 2. So x is approaching 2. It starts off at 1.2, and then it becomes 1.4, and so on until it actually reaches 2. And so we're going to say x is approaching 2. Now I want to answer the question, therefore, what is y approaching? What is y approaching? All right, so, well, the only way to do that is by actually plugging these numbers in. So let's go ahead and plug them in. I'm going to do y equals 2 times, let's plug in the first number for x, which is 1.2, and let's see what we get. So 2 times 1.2 is 2.4, and 2.4 plus 1 is 3.4. So that's what y is approaching there. Why don't you guys pause the video here and see if you can get the answer for 1.4. So for 1.4, the y value turns out to be 3.8. At this point, I'll just go ahead and give you the answers for all the other ones, but I'm going to stop at 1.9. All right, so after plugging in all these numbers, y is going from 3.4 to 3.8 to 4.2 to 4.6 to 4.8. What number does it look like the y value is getting closer and closer to every time? Well, it looks like it's getting it's going to be a whole number. And so if I had to ask you what whole number does it seem to be getting closer and closer to, maybe you guys would recognize that it's actually approaching 5. And you can plug in 2 and get 5. But the point is that we're approaching 5. So here's what I want you guys to recognize. As x approaches 2, as x gets closer and closer to 2, y approaches 5. Now, let's see what that looks like on a graph really quick. Let's plot these points. 1.2 and 3.4 would probably be like right about, maybe like here-ish. And then 1.4 and 3.8, probably like here. And then 1.6 and 4.2 here. And then 1.8 and 4.6, like right about here. And then finally 1.9 and 4.8 here. So as you guys can see, as x is moving to the right, closer and closer to a value of 2, the y value is moving up closer and closer to a value of 5. And they're both approaching this point right here, which is what we call 2, 5. Now you guys might be thinking, Bailey, what are you trying to get to here, bro? You're just talking about plugging in numbers. Well, the point is I want you guys to understand we're not talking about just plugging numbers in and getting answers. What I want you to understand is we're talking about approaching. So as x approaches 2, now here's the symbol we use for approaches. As x approaches 2, y approaches 5. So as x gets closer and closer to 2, y gets closer and closer to 5. Okay, so that's what I want you guys to understand. Now, this is what we call a limit. A limit is what you are approaching, a limit is the y value that you're approaching as x is approaching some specific value. And here's how we write it. So what is the limit? And that's the word we use for limit, is lim. What is the limit of 2x plus 1? So we put that right here. What is the limit of 2x plus 1 as x approaches 2? And we put that right there underneath of it. And remember, that's the y value. So in other words, what y value are we approaching? And the answer is 5. And this is what we call limit notation. And basically what this means here, if I were to write this in English, is it means as x approaches 2, y approaches 5. And I want you guys to understand, I'm not saying x equals 2 and y equals 5. I'm saying what they're approaching, and that's what this means. It means what are we going towards? What are we getting closer to? Now, the reason that distinction is important is because in mathematics, there are some numbers you can't actually equal for a function. You're not allowed to plug those numbers in. They're outside of the domain. But what you can do is you can approach them. You can get closer and closer to them. Now today, there's another thing that we can't ever actually reach, but we can sure as heck approach it. And what we're going to be looking at today is going to infinity. You'll never get to infinity. It's infinitely far away, but you can approach it. And so we want to talk about limits today, because limits tell us what we're approaching. As x approaches 2, y approaches 5. The word limit tells us we're doing a limit, which means we're approaching. And this tells me what function we're applying it to. But the main stuff we're focusing on is what is, as x approaches 2, what is y approaching? Okay? And that's what we call limit notation, and limits tells us what we're approaching. Gosh, Bailey, if you say approaching one more time, I'm going to have to stab my ears with a Q-tip so I can't hear you anymore. Sorry. It's a skill of teaching. If you repeat it enough, people eventually learn it, right? Okay, so here we go. Here's my limit notation. The expression above means that as x approaches c, y approaches L. So there it is. All right? And the function that we're working with goes here. Now we're going to make a little bit of use of that later on. But for now, I want to talk to you guys about what is end behavior. What is end behavior? The end behavior is the vertical direction of a polynomial as x moves to the left or as x moves to the right. So, let me see if I can give you a great example here. Let's say I have a polynomial, f of x. And let's say I want to pick some values for x for it, okay? So let's just go ahead and say I plug in -3, -2, -1, 1, 2, 3, 4, 5, 6, 7, 8, 9. And it's just going to keep going. But I'll start at -3, okay? Well, let's say that I decide to start here at -3, and I plug in my -3 for x, and I get a y value that looks something like this. And then I plug in a value for -2, and I get a y value that puts me maybe right about here. And then I plug in -1, and I end up right here. And then I plug in +1, and I end up here. And then +2, and I end up here. And so on. And I'm just going to keep going. All right? So, in this case, let's just say I go on forever. I just keep on plugging in bigger and bigger numbers for x. So in that case, my x value is approaching infinity. I'm just going to keep going forever. I'm never going to stop. So now my question is, what is y approaching as I do that? In other words, what's the limit of this function? What's the y value of this function as x approaches infinity? Well, let's take a look at the y values. So it starts down here at negative, and it comes up here to 0, and then bounces back down, goes back into the negatives, then it bounces back up. And then after that, it doesn't seem to stop going up. It just kind of keeps going higher and higher and higher. The y values just start going off into infinity. Well, this is what we call end behavior, okay? It tells us what happens at the end, the infinite end of my function. At the right end of my function, as I go to the right, the graph goes up, okay? But you can also talk about the left end behavior, not just the right end behavior, but let's talk about the left-ended behavior, okay? So now the question becomes, what is my, as x approaches negative infinity, that means as I go to the left forever, what is my y value doing then? Well, let's say I plug in a number and I just kind of keep plugging in more and more x's. And I see that no matter what I do, that y value just kind of keeps, the graph just keeps dropping. So in that case, as x goes to negative infinity, meaning as I move to the left, the graph starts going in a downward direction, which means the y values are going downward. So the y is going down into negative infinity. So now there's different outcomes you could possibly have, but this is what we call end behavior. It tells you what happens at the ends. On the left end of my graph, we're going down. On the right end of my graph, we're going up. Now, you need to be able to see that in the equation too, so let me circle that and say the same thing again. On the right end of my graph, we're going up. On the left end of my graph, we're going down. Okay? So here's another way that I can write these limits for you to understand when we're talking about end behavior. That means on the right side, we're going up. This means on the left side, because x is going to negative infinity, that means we're going left. And this is a y value, and when y is negative, that means we're going down. So that means we're going down. But I only drew one type of graph. Other things could happen too. For instance, as I go to the right, my graph doesn't have to go up. It could go down as I go to the right. For instance, if I had a graph like this, as it goes to the right, the graph could go downwards. Here's another one. What direction does this mean? X is approaching negative infinity. Hopefully you recognize that means we're going to the left. Well, it's also possible that as you go to the left, you don't have to go down when you go to the left. When you go to the left, you could also go up. Why not? Okay, so that might look like this, for instance. So the point is that you can never reach infinity, so we have to describe this stuff with limits. Limits tell us what we're approaching. We can approach infinity, but we can never get there. And here's what I want you guys to get. When the infinity sign here is positive, that means we're going to the right. That's the right side of our graph. And when the infinity sign here is negative, that's the left side of my graph. We're moving to the left. This number here is the y value. So when that one's positive infinity, that means we're going up. And when it's negative, that means we're going down. Okay? So remember, one's the x value, one's the y value. For x's, negative means left, positive means right. But for y values, positives mean up and negatives mean down. All right, so that's what we call end behavior, and that's how it connects to limit notation. It just basically tells us what the right side of our graph is doing and what the left side of our graph is doing. Okay, So let's take a look at example 1 here. Use limit notation to describe the end behavior of each function. Now, when I made these, I didn't put arrows, so I'm going to go ahead and put arrows on these now because the point is they go on forever, right? And I don't want us to miss that fact. So the arrows mean it just keeps going. All right, so I want to know what's happening on the left side of my graph and on the right side of my graph at infinity, okay? So now here's how we write that. If I want to write, I'm just going to make up a name for these. I'm going to call this one f of x. I should have done that. But I'm going to find the limit of f of x as x approaches positive infinity. Now that's going to tell me what's happening on the right side of my graph. So now on the right side of my graph, is it going up or is it going down? It's going down, so that would be negative infinity. So as I move to the right, my graph goes down. Okay, now let's describe what happens on the left. So for that one, I'm going to write the limit as x approaches negative infinity. So what's happening on the left side of my graph? Well, that looks like as I move to the left, the graph is still going down. So that's going to be negative infinity also. So on the right side and on the left side, my graph is going down on both ends, okay? And that's the end behavior of that function. That's what happens at the infinite right and the infinite left side of that graph, all right? Let's go ahead and take a look at the next one. So once again, I want to describe what's happening on the right side of my graph. I'll call this one g of x. And I also want to know what's happening on the left side of my graph. So let's take a look at what's happening on the right side of my graph first. It looks like it's going down, so I'm going to put negative infinity there. What's happening on the left side of my graph? Well, that arrow is going up, so that's positive infinity. Okay? And so that's how you're going to be using limit notation to describe the end behavior of a function. All right? So let's have you guys give that a try. I'm going to give you guys the same instructions. I'm just going to give you some different graphs to work with here. So suppose I give you this. There's one function. We'll call it h of x. And then here's another function. We'll call it m of x. Okay? So go ahead and use limit notation to describe the end behavior of these polynomials. Okay? Pause the video here, and when you unpause it, you'll see the solutions. All right. There you guys go. Now, just so you guys know, not all functions go up forever or down forever as you move to the left and right. Now, we're not going to talk about these in this chapter, but I just thought I would kind of introduce them to you for a second. Exponential functions look like this. Let me rewrite this. Exponential functions look like this. Now, if I were to, and you don't need to write this, just watch. If I graph this function, it looks like this. Now, the reason it looks like that is because there's an imaginary line here called a horizontal asymptote, and it's never allowed to cross it. So for this graph on the right side of my function, which is e to the x, it is going up forever, right? But on the left side, as x goes to the left forever, it's not going to go, the y value is not going to negative infinity. It's never allowed to cross that line. What is the y value of this line? The y value of that line is 0. So as the graph moves to the left forever, the y value gets closer and closer to 0. It doesn't go into infinity. Now, if you don't understand that yet, that's okay. We'll talk about it later. It has nothing to do with Chapter 6, which is what we're on right now. We will get to it later, though. But for now, polynomials, they either have positive infinity or negative infinity on the right and left-hand sides. They don't have any boundaries that they reach, so to speak. All right. So that's how you do it with graphs, but now let's think about it in terms of equations, because actually there's some characteristics about equations that are kind of interesting here. All right, so want to show you guys what effect the x squared, the square on this function, has on the outcome. So what I'm going to do is I'm going to plug in some positive numbers here, but I'm also going to plug in some negatives. Now let's plug this in. What is 2 to the second power? If I plug in 2 for x, I get 2 to the second power, which is 4. So my y value would be 4. Let's plug in 1 to find the next y value. It's going to be 1. If I plug in 0, I get 0. Now this is where something interesting happens. What happens if I plug in negative 1? Well, if you plug in negative 1 and you square it, what happens? It becomes positive. And what if you plug in a negative 2? Same thing, it's positive. So what happens is you get the same answer twice. Now, what does that look like on a graph then when I graph that? 2, 4 is the same thing as negative 2. It's also 4. So positive 2 and negative 2 both give you a positive 4. What if I plug in a positive 1? We get 1, right? Well, the same thing happens if you plug in a negative 1. You also get 1. The result of that is that on the right side of my graph, the graph goes up. But since the square cancels out the negative, the left side also goes up. They do the same thing on the left and right hand side because of the square. So here's what I want you guys to walk away from with this slide. Anytime you have an even power, the left and the right hand sides are going to do the same exact thing. Whatever direction the right side goes, the left side is going to go in the same direction, because the left side is just the negative version of the right, and the square cancels out the negatives. So you end up with the left and the right hand matching. But I put this one over here now with a negative in the front. Now the reason I did that is because you're going to see the outcome here. I'm going to plug in the same numbers. Now if I were to plug in positive 2 this time, 2 gets squared, but that negative doesn't. That negative stays there. So you actually end up with a negative 4. And if you plug in a 1, you get a negative 1. 0 stays as 0. What happens if you plug in a negative, though? Let's plug in a negative. Well, the square cancels that negative, so it's just positive 1 again, but that negative is still there, so that's also negative 1. Same thing happens when you plug in negative 2. You get negative 4. So once again, the right side and left side end up being identical. Let's graph this to see it. At positive 2, when x is positive 2, y is negative 4. But as you can see, the same thing happens at negative 2. When x is negative 2, y is still negative 4. At positive 1 for x, the y value is negative 1. At negative 1 for x, the y value is still negative 1. And 0, 0 is here. So here's what I want you guys to notice about this one. Notice that the right side's going down, and the left side's also going down. So once again, our little rule holds. Anytime your power is an even number, whatever the right side is doing, the left side is doing also. But the number in the front has an effect. If the number in the front is positive, it looks like they go up. But if the number in the front is negative, they go down. Okay? So, I want to summarize that really quick in a chart for you guys. So let's do that. Find this chart in your notes and let's do it. When you have an even exponent and a positive coefficient, that means the left side and the right side both go up. And if you have a negative coefficient, that means the left side and the right side both go down. And the reason they both go in the same direction is because the even exponent cancels out the effect of the negative. But the negative coefficient determines what direction they're both going in. All right? So let's keep that in mind. And let's move on to another thing. What if the exponent is odd? What if we have an odd exponent? Well, let's see. I'm going to plug in negative 2, negative 1, 0, 1, and 2 again. Let's see what we get. If you plug in negative 2, negative 2 to the third power means negative 2 times negative 2 times negative 2, and that's negative 8. The negative didn't cancel. If you plug in -1, you're going to get -1. If you plug in 0, you get 0. Now let's watch what happens when I plug in a +1. If you plug in a +1, 1 to the third power is 1. What happens when you plug in 2? Well, if you plug in 2, 2 to the third power, 2 times 2 times 2 is +8. So as you guys can see here, if you have an odd power, the negatives don't get canceled. Now let's see what that looks like on a graph then. At -2, we have -8. At -1, we have -1. 0, we have 0. 1, though, is a +1, and 2 is a +8. So now, as you guys can see, the left and the right-hand sides are going in opposite directions. They're going in opposite directions. Okay? So here's our new conclusion. Whenever you have an odd power, since the odd keeps the negative there, the right half of our graph, the positive side, will go up because you get positive answers. But the left side of our graph will give us negative answers. So the left side is going to go down. And so they do the opposite. So anytime your powers are odd, your ends are going to go in opposite directions. Okay? The negative goes to the left side goes down, the right side goes up. But what do you think happens if I put a negative in front of that? I'm just going to go ahead and plug it in. I'll do one example, and then I'll let you guys just kind of assume the rest. So we've already figured this out, right? -2 to the third power is -8. But if there's a negative in the front, that's going to switch it to being positive. And so if you keep plugging these in, this is what the result's going to look like. It's going to be the flip, the reverse of the other one. Let's graph it and take a look at it. So left 2 goes up 8, left 1 goes up 1, 0, 0. Right 1 goes down 1, right 2 goes down 8. So I want you guys to notice something that stayed the same. Since my power is odd, the left side and the right side are still going in opposite directions. But what changed was which one's going up and which one's going down. The negative causes the opposite thing to happen. So unlike over here, when you plugged in a negative, you got a negative, so the left side went down. On this graph over here, because there's a negative in front, when you plug in a negative, you get a positive, so the left side actually goes up. All right? And so I want to summarize these results now in our table as well. So let's go back to that table, and let's finish it. We had this before. When you have an odd exponent, they do opposites. They go in opposite directions. If the coefficient is positive, right goes up, left goes down. But with an odd exponent, if the coefficient is negative, left goes up and right goes down. Okay? So here's what I want you guys to therefore walk away from this. The leading coefficient of a polynomial and its exponents determine what the end behavior will look like. Okay? So let's go ahead and take a look at an example here. So last time we did this type of a problem, we found that we were looking at graphs. But for number one, I'm not giving you a graph. I'm just giving you the function. But that's all that you need. Okay? So number one says, complete each statement below and sketch the right and left-hand behavior of the graph of each function. So using your table, here's what I want you guys to do. Let's start by sketching the picture first. Okay? I want you guys to notice that my coefficient is negative and my exponent is even. What does the left and right-hand sides look like? Well, look at your chart. See if you can figure it out. Now I know that since the power is even, I know they're both going the same direction. They're either both going up or they're both going down. But the negative tells me which one it is. They're both going down. So on the left side of my graph it goes down, and on the right side of my graph it goes down. So now that I've sketched my graph, I'm ready to answer this. What does this mean as x approaches infinity? What side of my graph am I talking about? I'm talking about the right side. And on the right side of my graph, which direction is my graph going, up or down? It's going down. So therefore I'm going to put negative infinity here. All right? And that's it. Let's do another one. We got that one taken care of. Let's try the next one. 3x to the third. Look at your chart. See if you can sketch what the end behavior looks like. I'm going to draw a line here to separate the first one we did from this one. Look at your graph, your chart that we copied earlier, and see if you can sketch what this one would look like. I have an odd power here, and when I have an odd power, that means the right side and the left side go in opposite directions. I have a positive coefficient. When I have a positive coefficient, that means that the right side goes up and the left side goes down. Now, what side do I care about to answer this question? That means I care about the left side. So what's happening on the left side of my graph? The left side of my graph is going downward. So that's a negative infinity also. Let's do another one. See if you can sketch the picture of this next function. What would that be? Since I have an even exponent and a negative coefficient, it's like number one. It's down on both sides. What side of the graph do I care about? The right side. What's the right side doing? Going down. Last one there. See if you can do all of those things all by yourself real quick. See if you can find what goes in the blank and sketch a picture. Since I have a odd exponent and a negative coefficient, it's up on the left, down on the right. And I care about what's happening on the left side this time. So in this case, I have positive infinity, because on the left side, it's going up. All right, number two. Use the graph of that. So A represents the coefficient and N represents the power. And it could just be anything, but here's what the graph looks like. So I really don't want you guys to know what the equation is, but I just want you to know what its graph looks like. And here's what it looks like. Use the graph of the function there to complete the statement below. The coefficient must be blank, and the exponent must be blank. Well, as you can see, it's up on the right and down on the left. Now, they're going in opposite directions. So I know that my exponent should be odd. What do I know about the coefficient, though? Because when you have an odd exponent, it could be down on the left, up on the right, or it could be up on the left and down on the right. In this case, since I have up on the right, down on the left, that means my coefficient must be positive. Okay? So it's like this one here. Up on the right, down on the left. So I have a positive coefficient and an odd power. All right? Okay, so that is doing end behavior with equations instead of just graphs. Let's go ahead and have you guys pause the video here and see if you can complete all of these blanks. And don't forget to sketch your little graphs here on the side. All right, guys, so there's your answers. I circled the arrows for the first few problems up there so you know which side we should be looking at. And from there, I'll let you guys ponder it and let me know if you have questions, but that's the end of that. Okay. One more topic I want to share with you before we call it a day with this lesson. Let's talk about the battle of the terms. What the heck is Bailey talking about here? All right, so they start off in their corners, and we want to see who is the heavyweight champion. Now, they both look like they're a pretty good match, right? They both have a 3 and a 1, but they've decided to put their numbers in different places. We're going to see who's the more powerful opponent here. So the one in the top left, opponent in the top left corner, has a 3 coefficient and a power of 1. But the opponent in the right-hand corner has a coefficient of 1 and a power of 3. So let's see who's going to win this fight. All right, in round 1, ding, ding. What happens in round 1? Well, in round 1, we're going to go ahead and plug a number in for x. So for round 1, I'm going to plug in 1. So I'm going to plug 1 into my opponent in the left corner. And then I'm going to plug 1 into the opponent in the right-hand corner as well. And we'll see who wins round 1. Well, if you simplify this expression, you get 3. And if you simplify this expression here, you get 1. And the crowd goes wild because this guy won round 1. He came out with a bigger answer. All right? Let's go ahead and check out round 2. Ding, ding. All right, so in round 2, we're plugging in 2. Let's see who wins this battle. 3 times 2 is 6. 2 to the third is 8. Oh! Opponent in the right-hand corner makes a lively comeback, and he takes the title for round 2. All right, let's go ahead and check out round 3. Let's see who's going to win round 3. This will be the tiebreaker. Here we go. Who do you guys think is going to win? Bailey, you're lame. I know, it's okay. And you know what's even worse? Is I'm doing this all by myself in my classroom right now. Awesome. All right. 3 times 3 is 9. 3 to the third power is 27. Whoa, looks like this guy in the corner over here won big time on that one. That's a knockout. Now, here's what's my point with this, you guys. Even though they both had the same numbers, 1 and 3, this guy, he might not be so powerful in the beginning. But as time goes on, he's going to win. And the reason for that is because an exponent is more powerful. And that's why we call them powers, right? Well, I'm assuming maybe that's why, maybe not. But there it is. So the bigger the power is, the more powerful that term will be. That doesn't mean that these guys don't matter. Like, he did pretty good in round 1, didn't he? He won. So they have an effect. They do something. It's just that in the long run, they don't win. These guys win. Okay? So now, what are we going to do with this fact? What does this have to do with today's lesson and end behavior? Well, let's see. Let me ask you this. When we're talking about end behavior, we're talking as x approaches infinity. So as x gets bigger and bigger and bigger. Now in this case, my x was the round we were in. So if I keep increasing the round, who's going to win? This guy is. And so what that means is that at infinity, as x goes to infinity, this guy is the one who really determines what happens. This guy can have an effect on things in the short run, but in the long run, this guy is the one that determines what happens at infinity. Because as we plug in bigger and bigger values for x, that's the one that has the biggest effect. So today we've been looking at problems that just look like this. It's just one term with a coefficient and a power, and we've been talking about what's its end behavior. But as you guys know, polynomials don't usually have just one term, they have a whole bunch. Okay? And so my question to you is, as we plug in some numbers for x, all of these guys are going to have some effect. This guy's going to have a pretty big effect at first. That's negative 100. He's going to really determine what happens to the outcome. This guy will have an even bigger effect because he gets multiplied by x. And this guy, and this guy. But ultimately, this is the guy who determines what happens to this polynomial. Okay? So this is the one that we look at to find out what the end behavior is. These guys will tug and pull on it. You know, so as I'm plugging in points, even if I plug in 1 here, I get 7. But this guy's minus 100. So even though I get 7, if I take 100 away from that, I end up with negative 93. So I'd be way down here on my graph because of this guy. But by the time I get to a place of plugging in 10, by the time I plugged in a positive 10, I should have put that over here, sorry. By the time I plug in a positive 10, do you guys know what 10 to the 4th power is? That's 10,000. If you multiply that by 7, it's 70,000. Who's more powerful, the 7 to the 4th or this guy? By the time we get to 10, the graph's off the chart on the right side. So on the right side of the graph, we're going up because of this guy. Even though this guy's trying to pull us down, it doesn't matter. This guy determines what happens at the right side of our graph as we go farther and farther to the right. And so that leads us into our final conclusion here. So you guys can just circle this on your notes if you want to. Here we go. So suppose I have this function here. F of x is equal to 5x to the 5th minus 2x plus 10. Which of these terms is the most powerful term? Which of these terms is the term that will determine the end behavior? Hopefully you know it's this one because that's the one with the biggest power. So the limit of this function as x approaches infinity, that's going to be the same thing as the limit of just 5x to the 5th as x approaches infinity, because this is the one that really determines what happens. So even though the function represents the whole thing, we really only care about this piece here, the front piece. So now that we know that, what is the answer going to be? Well, odd power, positive coefficient means up on the right, down on the left. Since we care about the right for this, the answer is positive infinity. Okay? So, if you want to find the end behavior of a polynomial, all you do is you look at the first term and then do what we've been doing for the rest of the day. Let's go ahead and take a look at number 2. So what's the limit of my function at negative infinity? Well, that's going to be the same thing as the limit of just the front term there at negative infinity, because that front term is the one that really determines what happens. So what happens? Well, same thing. It's up on the right, down on the left, but this time I'm looking at the left side. So the answer will be for this one, since it's going down, negative infinity. Okay? So same thing that we've been doing. We just have the extra step of knowing that when you have a full polynomial, all you have to do is just pay attention to the front term. And other than that, you're good to go. All right, so last example here. Here we go. Your turn. It says example, but it's actually student practice. I'll change it right now. Go ahead and pause the video here and see if you guys can find the answer. When you unpause it, you will see the solution. Okay, so the term that we care about on this problem is, of course, the one with the biggest power, which is 2x to the 6th. So the limit of the function at infinity is the same thing as the limit of the function at of negative 2x to the 6th at infinity. When you have a even power and a negative coefficient, this is what your graphs look like here, going down on the left and on the right. And since we are approaching positive infinity, we care about the right, and that's going in a downward direction. So the answer to the first one is negative infinity. And whenever you do the same thing when you go to the left, we just look at the left side, and that's also negative infinity because it still goes down. All right? And that concludes our lesson on limit notation and end behavior, and we'll see you guys next time.